Hello, everyone. Uh, Welcome to another session of University of Toronto Robotics Institute seminar series. And I'm very glad to have all of you uh, today. And we have a distinguished speaker, Ken Goldberg, with us. Uh, Ken is a William S. Floyd Distinguished Chair in Engineering at Berkeley and an award-winning roboticist, filmmaker, artist, popular public speaker in both AI and robotics, and also my advisor. Uh, he has published uh, many papers, too many to count, and has won many awards. I think I will not waste time by listing all of them. He has won over 10 Best Paper Awards just in the last 5 years. And he recently also won the IEEE RAS George Saridis Leadership Award in Robotics and Automation. Interestingly, aside from the technology work that he does, he's a pioneer in technology and artistic visual expression. And did you know that he has had over 70 art exhibits? And even more interestingly, he has built or made documentary films where he has been co-writer, which have been selected for Sundance and also a nomination for the Emmy Awards in 2014. He is truly someone who has bridged the two cultures of art and science. And as a personal note, he has taught me how all scientists are actually artists under the cloak, where we are all operating at the boundary of contemporary knowledge and tinkering to create something new. With that, without further ado, I'd like to welcome Ken Goldberg and would love to hear what he has to share on the latest wave in grasping. Ken, all yours.
Thank you so much, Animesh. I really appreciate that. It's such a pleasure. I'm glad that you pointed out my major achievement, which is to being your advisor, and a major accomplishment, I should say. Let's see. Can you see the screen? Is it the video moving? Uh-oh. Now I'm worried that something went wrong.
No, I think everything.
You can see it?
Yes, everything works.
Okay,
great. It's great.
All right. Thank you, guys. Thank you for being here. So what I want to cover today is what I call the new wave in robot grasping. And I always like to start with this this video clip from Iron Man, and Animesh and other students have said over the years that this was a big inspiration for them to get them interested in robotics. And I love this scene in particular because that's kind of exactly where we are right now. Robots are still incredibly clumsy. Now, I want to also just put a shout out to my lab, my students. This is a cartoon from a book that we put out last year, a kid's book to get kids interested in robotics. And these are some of the actual real robots in the lab. These are the real students in the lab who do the real work. And there are 4 postdocs, 8 grad students, and about 25 undergrads now working in the lab, doing incredible work. So what I'll do is cover the new wave in the context of what I call the first, second, and then the new wave, and then also talk about some new projects that we're just submitting. So let's start by going back in time, 2,000 years to ancient Athens, and look at this picture by Raphael, where he's pointing out he's capturing all the great thinkers of the time. And there's the philosophers, the writers, the artists, the engineers, the scientists, the astronomers. And in the center of the picture is Plato and Aristotle. And what's really important to understand is that the positioning of the hands is very crucial here. So the hand pointing up from Plato is going to reflect his philosophy. And he believes in the perfect forms and the ideal forms. You must start up at the top with pure axioms and then work your way downward to understand reality. And his student on the right is Aristotle. And Aristotle actually believes quite the opposite. He says you must start at the ground and then work upward to understand the world by collecting lots of information and then building taxonomies, etc. By the way, this isn't the first time that a brilliant scholar has disagreed fundamentally with his research advisor. All right, so now let's talk about grasping and the hands, what they do, and human hands are quite incredible. Humans have an amazing dexterity, and they can pick up almost any object with ease and manipulate it. But as you know, robots is not the case. Robots, despite 70 years of robotics research on grasping, robots are still incredibly clumsy. Now, if we could figure this out and solve it, it would have great benefits. For example, wouldn't it be great if you could, this is typical. You go off to work, and this is your house in the morning, and then you come back, and it's all nicely straightened up. That would be fantastic. And another area that would be very helpful is this, and this is actually a real photo outside my house, and I think everyone can relate to this, especially now, is that that we have a huge challenge with e-commerce, and the sales of e-commerce have been growing steadily over the last decade, but this year they skyrocketed, and it was due to COVID-19 and the fact that people were essentially didn't want to go out much, and second of all, there was just a huge this adoption, and it snowballed. Now, here's the challenge is that what's behind the scenes when you order things, as most of you know, is that the orders have to be put together from these warehouses, and this is essentially a manual job. And this is what it looks like in an Amazon warehouse. And the other issue that you're seeing here is the proximity. This year, because of COVID-19, people didn't want to work in these kind of environments. They were too close, so they had to space the human workers out. And so there was a real limited supply of workers and a massive increase in demand. So the grand challenge, as Rod Brooks has put it very nicely, is that if robots could grasp arbitrary objects, anything you put in front of them, like you see here, this is what you see in a warehouse, if we could do this, it would have significant impact in factories, homes, and warehouses. Now, let me address the issue of hardware for a moment. And I know that there's really interesting and exciting work going on in robot grasping with hand design, but I want to argue in favor of very simple hands. This is the classic parallel jaw gripper. It's the workhorse of robot end effectors, and it can actually do almost anything. So I want to argue that here's an existence proof. The surgeon is operating this. It's teleoperated, by the way. We're not at the point where this can be done automatically, but a surgeon with a very simple grippers, parallel jaw grippers, can do very, very complex things. And another proof example of this is chopsticks. Again, very simple hardware, but they can be used, if they're controlled properly, to pick up almost anything, even very slippery, irregularly shaped objects. Now, another thing I want to talk about is sensing. So a big change in the last decade is in depth sensing. And as you know, LiDAR has had an enormous effect on work in self-driving vehicles. It's also being used in this problem of warehouse grasping. And I just want to point out that it is an important advance, but it's not a silver bullet. So if you look at the image on the right, I just want to show you that the point clouds you get out of a typical depth sensor are not perfect. There are gaps and holes, and this is due to the light not reflecting in the way that it might be expected. And this is exaggerated when there are areas of high curvature or transparencies or specularities in metallic objects. So that's a big problem and something we have to overcome. Another problem is the physics. So let me illustrate that. Here we're going to just have this robot push a bottle across a table, and it's basically we set this up as close as possible each time the same way, and the robot motion is exactly the same in each case. But the outcome, as you can see, is extremely different, and this is due to the uncertainty in the underlying surface friction. And I would even say it's non-stationary, because as you're pushing the object, it encounters different aspects of the surface friction. This is a very, very minute change. Just a grain of sand under there will cause a dramatic difference in the final orientation of the object. Now, I want to say that this is a hard problem. We can predict the motion of an asteroid 1 million miles away far better than we can predict the motion of pushing an object across their table. In fact, I would even go to say this is an undecidable problem. Knowing how the object is going to react is not something that with better information we can resolve. It's aleatory uncertainty. It is undecidable. Okay, so with all that, this is the challenge. We want robots to come in and clean up after a dinner party, but let me give you a sense of what it's like to be a robot. Okay, all your sensors are noisy and imprecise. Your actuators are also not perfectly controlled. So there's some error in your actuator movements, and there's uncertainty in the physics. So it's not completely surprising that robots today are still incredibly clumsy. So again, I want to just emphasize this point that there's uncertainty in the physics itself, in the perception, and in the control system that all combine to provide a great amount of uncertainty at the robot gripper. And a small amount of error, very small, even a millimeter, can make the difference between holding something securely and dropping it. Okay, so hopefully I've convinced you why this is a hard problem, an interesting problem. So what do we do about it? So roboticists have been looking at this for many years, as many of you know, and the what I call the first wave was really very consistent with Plato. It starts with axioms and tries to deduce models of reality. And this goes all the way back to the 1850s, even further, with the great mechanicians of the world who were designing clocks and other devices, and they had to understand the kinematics of machinery, wrench mechanics, etc. And many roboticists have followed in their footsteps to develop analogous models for robots. I had the good fortune to work with Rujna Baichi and Shankar Sastry, who wrote the foundational textbook on robot manipulation, and where it's a wonderful book. Many of you are familiar with it, and it goes into great detail on these kind of models. They're analytic methods that basically look at the placement of all the forces and torques and surface normals, and then make a decision, which is a binary decision, whether or not the object will be held securely. So for some state of the contacts and the grippers, there is an outcome. Either the object is immobilized or it is not. And what we want to do is find a configuration of the contacts that will immobilize the object. That's what I'm showing with U star there. Now, if you go into the Handbook of Robotics, the recent edition, there's a chapter on robot grasping. And so it's a great chapter. It covers this very, very nicely. It's about 40 pages. And if you get to the very end of it, you'll find a sentence. When a robot identifies an object to grasp, its knowledge of the object's pose and geometry are not perfect. Now, this is only mentioned at the very end of the 40-page chapter. I consider this one of the greatest understatements of all time. I mean, this is such a huge matter, but it's totally not considered until the very end. And this is this uncertainty that I'm talking about. And the first wave essentially ignores it. It says, we know everything. We know exact precise shape of the object. We know where all the contacts are. And that's what allows us to develop this beautiful mathematical machinery that can determine where things are. Okay, but that's not, that doesn't quite work. Well, we started developing a model for this to capture uncertainty, and this was the beginning of Jeff Mahler's PhD thesis. He's contemporary with Animesh, and Animesh was involved in some of this work as well. And we call it the dexterity network, for a reason I'll explain, or DexNet. And the idea here is that that there is uncertainty. So we're going to treat it in a statistical way. We're going to consider all these variables as random variables. And now we have a graphical model where we can talk about where the sources of uncertainty are. So we have distributions around the true pose of the object, the shape of the object, where the gripper, the contacts are, will be determined by the gripper and the shape. The surface normals will be determined by that. The center of mass is also not known precisely. The frictional coefficients are not known and they're changing. And all this leads to uncertainty in the precise forces and torques on the object, and that will affect whether or not it is that a particular commanded grasp will be successful or not. So what we're showing here is that you have uncertainty, so you have these random variables in both the state of the object and the state of the gripper. Now, what we can do with that is we can sample from these distributions and then try to estimate the probability that a particular commanded grasp will succeed or not. And to give you intuition for that, let's imagine we're trying to grasp this, this object here shown in red. It's pipe fitting. And it's very typical. It's a CAD model, and it has maybe 1,000 facets. Well, a grasp is defined by 2 contacts on that surface. So that means there are 1,000 squared possible grasps, 1,000,000 possible grasp configurations. So what I want to do, though, is I want to find ones that are robust. In other words, they are tolerant of these uncertainties. And what I mean by that is shown here. I have a nominal grasp, and then what I'm doing is I want to start to look at small perturbations on that grasp and sample from these distributions. So I'm varying the pose of the object, the pose of the gripper, the center of mass, and all of these variables. And for each one, I'm checking, will it succeed, using the classic wrench mechanics. So I'm not throwing that away. I'm using it, but using it in a stochastic model. And so then we can check, and we can do a number of samples, and then we basically are doing a version of Monte Carlo integration here to estimate the probability of success for a particular nominal grasp. So the outcome might be something like this, where on the left, we have a very low probability of success for this, and on the right, very high probability of success for this one. And hopefully that's intuitive to you as well, because the one on the left is sort of unlike, you can imagine a very small error will cause that part to move away, whereas the one on the right is almost self-aligning. It tends to sort of close in and scoop up the part, even if there's small uncertainty. So that's why it has a high probability of success. Now, we implemented this in what we called DexNet 1.0, and the idea was we took images using depth cameras that I mentioned earlier, and we then estimated the state of the pose of the object, that's X, and then we use this, we apply the Monte Carlo analysis to basically find the best grasp, the grasp that has the highest probability of success. And let me show you it working. So not so much. All right, what happened? Well, the problem here is that it computed a beautiful, robust grasp, but the state was wrong. So it thinks the object was actually in a different configuration, and it executes a perfectly robust grasp, but for the wrong state. So this does not always work. And the issue is perception uncertainty. And so now we have another issue here we really want to model. Remember, we sort of started with the 3D camera image, and then we use that to estimate state. But we have to actually learn a better way to do that, and we have to do that more systematically. So now what I want to do is that I'm given an observation, Y, which is in this case a point cloud or depth map, and then I want to plan the grasp that will maximize the robustness or the probability of success. And this really leads us to the second wave, where uncertainty and in perception comes in. And this is where this distinction between Plato and Aristotle comes back, because remember, Aristotle was arguing in favor of a very different approach to making progress in the world, and it was to look down at all the plants and animals and rocks and minerals and build up models from data. So his point was collect data, and that is essentially the root of the contemporary wave in artificial intelligence, deep learning. It's data driven, and it's been extremely successful. And a number of researchers have been applying that to robot grasping, and it's accelerated since over the last decade. And one of the sources of that many very natural sources to look at real examples, to learn from experience in the real world. And so these can be either human labeled or there can be self-supervised model. In particular, you're probably familiar with the ARM farm at Google that set up a number of robots, 14 robots, to work around the clock to basically acquire data on grasping. And one thing I want to point out, though, is that if you look at the published results there, they were able, as it learns, this is a learning curve, it's able to reduce the failure rate, as is shown on the right. But if you look really closely, it says that after, this is a log scale, and it says that after about 10 million observation or examples, the system is at about 20% failure rate. Now, if you try and extrapolate out from that, it looks like, probably at 100, that's, by the way, a year's worth of round-the-clock data collection. So if you want to get down to 90%, looks like you're going to need another 10 years of data collection. And if you really want to drive it down to 95, you might be looking at 100 years. So my point is that this idea is that the system, by collecting data, you need a great amount of data. Now, I want to speaking of data, look at the example of computer vision. And computer vision, as you all know as well, has been has made extreme amount of progress with systems that can identify objects in a scene. This is from a James Bond movie. Now, it's not perfect, but it's really made enormous progress, and it's largely due to data sets. And ImageNet was the big example. It was a huge breakthrough. Fei-Fei Li and her colleagues developed this ImageNet, this data set of millions and millions of images, but they were hand labeled, drawing bounding boxes around objects and then labeling what those objects were. So I'm curious, that my hypothesis is, could we do something similar with DexNet, with robotics? Sorry, and we'll call that, instead of its ImageNet, we'll call it DexNet. And the idea is to come up with lots of labeled examples. And in this case, we're labeling them not with a name of an object like a necktie, but we're labeling the objects with robust grasps that we're pre-computing. And so this is the analogy, is that can we generate a very large data set that would get us to a critical mass where we could start to see the system generalizing to new objects. And in the same way that ImageNet reached a critical mass, and again, once you had that, you could learn a very large neural model, convolutional neural net, that would then be able to generalize to new examples. And so we set out to do this, and the good news is that there's a lot of 3D models out there because of a number of examples. Now, in one is that a lot of people are publishing the 3D models for gaming. So when you look out there, you'll find lots and lots of weapons and aircraft. So we have plenty of those, but those are not very commonly found in warehouses. So we had to go out and really curate a data set of three-dimensional objects that were more natural in, let's say, warehouse and home environments. So we found objects like these. We cleaned them up. We made them airtight so that the surface normal properties are correct. We cleaned up we made them into regular solids, etc., and scaled them a number of factors like that. This was a fairly long process. We also augmented the data with blister packs. This is very common, and in warehousing and retail, is that you have objects that are attached to a piece of cardboard. So it's very easy to add that piece of a little planar surface onto the object and then use that as a new object. And then we also looked at what we call adversarial objects. And this, again, is somewhat inspired by the work going on in adversarial vision, computer vision, where they come up with examples that are very difficult. Here we wanted to find objects that were difficult to grasp, not obvious. So it took some time to find these kind of objects, but we've been collecting these objects. And then we put them together into a big network, because we want to have we want to understand relationships between them. So this leads us to the new wave, and I want to just do a quick shout out to a book that came out this year. It's called How to Train Your Robot, and it's available for free online on my webpage. My daughter Bluma is the first author. She's a very good negotiator. She wanted to make sure she was first author on this book. And it really tells the story, as I mentioned, about kids and gets them interested in robots. There's a scene in there. It basically tells the story about DexNet learning how to grasp objects. And in particular, trying to explain it to kids, came up with the analogy that it's like the robot was dreaming about how to grasp objects. And that's how it learned. In other words, not doing it physically, but dreaming about it. And so what I want to say is that the important distinction here is that we're now performing the grasps in simulation and then learning from many of the simulated examples rather than doing them with real robots. Now, the simulation is also a daunting amount of computation. So as I mentioned, if we do for each object, we might have 1,000 facets. That's 1,000,000 possible grasps. And then we might consider 1,000 perturbations for each grasp. So we're talking about 1 billion grasp evaluations per object. And if we have, say, 10,000 objects, then we're getting into a fairly large number of computations. We have to do 1 trillion grasp evaluations. So that can be actually parallelized very nicely. So we did that. We put it on AWS and spread them out. And then you could actually do this kind of computation overnight. Now, we also wanted to speed it up a little bit. Now, just a quick detour here. We found a fun idea, which was to use multi-arm bandits to bootstrap this. And the idea is to make use of similarity between objects and between grasps. And there's this idea of correlated bandits. And the key idea is first have to identify when you have two similar objects. So we built a network to do that, and we were building on this new, at that time, new idea of multi-view deep convolutional neural nets, that you could just take a lot of synthetic views of an object and then train a network to start to identify the object from different views and cluster those different views together as a similar object. And that worked very well. So that gave us a similarity measure that we can use in a kernel to control the learning process. So what we're doing is we're treating the probability of a grasp as being successful or not as a beta distribution. And we bootstrap that by we initiate it with the value of a nearby grasp. And then as we collect examples, we apply the examples again using the simulation, we can increment the alpha variable when we have a success and the beta variable when we have a failure. And that way we would tune the beta distribution, but it basically has a bootstrap, a prior that it can build on. And we found that actually works nicely. So if you have a fairly if you have an object, as you see on the left, it's kind of irregular, and then we don't have a lot of similar objects, the quality, the best grasp you get over time, and this is we're iterating to find better and better grasps, it doesn't get much better. But on the right, we have this object that looks like a spray bottle, and for 1,000 objects here, that's like the dashed blue line, it gets a little better than uniform sampling. But when you get 10,000 objects, well, now all of a sudden you have a number of similar objects in your data set. You can use those, and you see that really gives you a boost in being able to converge on high quality grasps. All right, now you may be familiar with the advance of open AI. They developed the robot, the shadow hand performing Rubik's Cube and being able to manipulate it. As you know, it's a very extensive process of using simulation like we have been doing. And they also adopted a technique that we've been doing, which was that they used what they call domain adaptation. This is exactly what we talked about earlier. They want to randomize the system and give it lots of variation. And this is essentially a key trick to crossing what you might call the reality gap from sim to real. So the idea is you have to inject noise. You have to make the system robust in simulation if it has any hope of working in reality. So we do this in terms of both the control, but also in the sensing. So what we're doing is we're generating 3D depth maps, and we're injecting noise into those that are consistent with the noise properties of the cameras that we use. So again, not just random noise. I really believe in structured domain randomization, where you are putting in noise that actually has the properties of your real system, your real sensors and your real controllers. And what we get out of that is a data set. And this is the set where you have combinations of an input image, Y, a grasp configuration, U, and then R, the estimate of the robustness of that grasp. So those triplets are then put into, basically generated, and they can, with using the cloud, can be generated fairly quickly, and you can come up with millions of examples. Both positive examples, grasps that are of high probability of success, and negative examples, grasps that don't. And then what we do is we take all that data set and we train a deep network. So we can basically tune these parameters in this large vector theta to minimize the loss between its output and the outputs that we have measured in the data set. And then once we do that, we have theta star, the best set of parameters. Then what we want to do is be able to say, okay, now given a particular value of the sensor data, Y, what is the grasp that optimizes the probability of success, picking up an object there? And so this is what we call the grasp quality convolutional neural net. You give it a depth map and a candidate grasp, and it just generates the quality. And then you use that in an optimization loop to optimize the quality. And so here's what it looks like. You want to execute the best grasp. And this is the another image of the system, but I'll just show you this running here. So it was very surprising. And I have to say this, when Jeff called me into the lab and said, let's look at how well this is doing, I was surprised. These are objects that it was not trained on, and it actually performs surprisingly well. And by the way, these objects, all the objects it was trained on were rigid. So it's starting to pick up things that were non-rigid. So it was generalizing very well. And that got us very excited. So the next thing Jeff did was he extended it to bin picking, which is a notoriously difficult problem where you don't have just one object in isolation, but you have a heap of objects in a bin. And what he did was the same thing, was to train it on synthetic bins. Again, like dreaming, not dreaming about picking up one object, but dreaming about bins and picking up objects out of bins. And you could train it very analogously. So this is the output. On the left, you see the color image. Next, you see the image of all the candidate grasps that it selected, and then it's iterating, basically feeding those through the network to choose ones that are better using cross entropy to then optimize. And on the right, it basically finds this grasp that it believes has the highest probability of success in that cluttered bin. And so here we go. Now it's actually working in bins, and we call this DexNet 2.1, and it's able to pick up things. Again, none of these have been trained on. They're all novel objects, and it's and some of them are deformable. So we released this. We got some really nice coverage in the press, and companies started to approach us about incorporating it. And one of the things that they pointed out was that they use a different kind of gripper, the suction cup. And now, remember, I was making a big point about simplicity. We were always using the parallel jaw gripper, which has two contacts. Well, the suction cup only has one. So it's actually, it turns out that's what we call unicontact grasping, and we just hadn't really considered that. So we started looking into it. And it turned out that we were surprised that there was very little literature on unicontact grasping and suction cups. In other words, to really model the physics and analogous to the beautiful literature that we had found for contacting with with parallel jaw or multi-fingered hands. So, and it may be out there. We still haven't found it. So if some of you are aware of it, please share it with us. But we started to develop our own. So the first step was to try to model the physics of the vacuum cup itself and this contact, the seal of the vacuum, which had to do with the local surface geometry. And generally it's not planar, so you have to look at how much it varies from planar, and then look at the conformation of the suction cup. And then you also have to think about a new model of the wrench mechanics, because suction cups are different than finger joints because they are contact between two jaws, because here you have the ability to resist forces orthogonal to the suction, but actually very poor ability to resist torques that will peel the suction cup off. So we had to model all that, but then once we had that, we have now a new analytic model, and we can throw it in and train on lots and lots of synthetic examples. So as you see on the left is a candidate suction grasp point on this object. We look at all the perturbations, just as we did with parallel jaw grippers, and on the right, it's computed a map of the robustness of different contact points for the suction cup. And it makes kind of, again, intuitive sense that these points in green are better places to put your suction cup. They have higher probability of a successful grasp. And in a bin, again, we did this in the bin context, you can do that as well. And so now, again, it's looking for points in a bin that have a high probability of success for a suction grasp. And then we put these together. So we call this ambidextrous, where the robot has two different kinds of grippers. It's got a suction cup on one hand and the parallel jaw gripper on the other. And so the suction cup can pick up a lot of objects, as you see here, but now we want to actually have them both working. So we call this composite policies that use both of these two modalities. And the key there is to put them into a common reward function, because you have to normalize these estimates. And that took a little bit of time, but basically you can see on the left, this is characterizing the grasp axes that will in their probability of success. And on the right, the suction probabilities and their how probable they are. And then we can essentially at any given time make a decision which of the two modalities have the higher probability and execute that one. So now the suction is trying to pick up things and the gripper is trying to pick up what it thinks it can. And it doesn't always work. So the suction can't see that this object is porous, but then it knows to be able to send over the parallel jaw gripper. So this has been very, very fun to watch this evolve. We have a paper on this at in Science Robotics, looking at this ambidextrous model. I also want to note that it doesn't always work. There's many objects that the system cannot pick up, and these are some of them. The objects could be too heavy. They could be just have a very irregular shape that the robot gripper can't get around. If they're transparent, often is really a problem. And on the right, you see the paperclip. So people sometimes talk about robots taking over with paperclips. Well, unfortunately, our robot cannot pick up a paperclip. Okay, the suction cup can't get on it, and it's too small for the gripper. So again, it's really important I believe, to keep our eye on these pathological cases. But we have also started a company, and so Jeff and three other of the students in the lab co-founded Ambidextrous Robotics, and our motto is getting a grip on reality. And we're actually coming out of stealth mode at the end of this month. So if you're interested in learning more about that, please get in touch with me. Okay, so this is these new waves or the three waves in robot grasping. And let's go back to the painting. And if you actually pull back a little bit in this painting, you actually see that there are many hands in the scene. And I think the message that's going on here in School of Athens painting is that if we really want to understand the world, it's not going to be just Plato or Aristotle. They are two very interesting and oppositional approaches. But actually, if you look around, there's many different approaches to understanding the world, as indicated by all these hands. So I think that's going to be the answer. And so we're making progress, but there's still many more open research problems. And by the way, if anyone really doubts that robots are going to take over, or that robots are going to take over and that humans are doomed, I'm not worried about that. As you can see here, human manipulation abilities are quite impressive. Okay, so now I'll just touch on a couple new projects, and then we'll open up for questions. And I'm really curious to hear questions from you. New projects, well, we have another paper that came out in November, and this is Jeff Ignowski's work. He's a postdoc, and he's been working on the second problem, which is once you have the object grasped, how do you move it very rapidly into a new location. And it turns out that you want to do that with a minimal jerk motions, but computing the minimal jerk motion is prohibitively time consuming. So you actually spend more time computing the minimal jerk than you save in performing it. But he was able to try something really exciting where he could generate lots of examples, again, in simulation, and then use that to build a neural network to do an estimate of the minimum jerk trajectory. And then that provides a warm start for an analytic method that then actually optimizes. And that turned out to do a dramatic speed up. So what used to take on the order of 10 or 20 seconds, he got it down to 80 milliseconds. So it's now practical for industry. Another project that I'm excited about is actually been led by two undergrads, Jennifer and Priya, who are tackling the problem of untangling cables. And this is a real problem in many homes, certainly, but also in a lot of industrial environments and repair shops and in boating, etc. And it turns out there's some really nice theory out there for how to knot theory, essentially, how to model knots, but it's essentially graphical. So the trick is, how do we then get to the graph? And they've been looking at these deep learning techniques to identify pin and pull points to learn pin and pull points by example, and again in simulation, and then be able to untangle structures like this. And we're looking at dense knots, that is, knots that are fairly tightly knotted, and we want to be able to have the system. And these are some successful runs of this bilateral manipulator. It's actually a surgical arm, picking up and basically loosening and untying these kind of knots. So, and we're also looking at dynamic cables. So we were inspired by one of my favorite movies, Raiders of the Lost Ark. And so we have a paper that it will be at ICRA in May. We're calling it Robots of the Lost Ark. And here the idea is to manipulate fixed endpoint cables. So you imagine that you're let's say vacuuming, and something gets the cable, the power cord gets stuck, and you have to sort of flip it to get around a chair or something. And people do this all the time, but can we get a robot to do it? So we've been studying that, again, using a combination of techniques. But the idea is we want to be able to perform a task like vaulting over an obstacle. We also look at what we call knocking, which is we place an object on an obstacle and we want it to be knocked over, or weaving. And this is to arrange the cable between multiple obstacles. So we're also working on robot-assisted surgery, and Animesh did a lot of this work when he was in the lab, and it's ongoing. We're looking at things like debridement, and especially when we look at environments that may be deformable, as mentioned earlier. And we have a Da Vinci robot arm in the lab that we use regularly for experiments. And another last project I'll mention is we call the Alpha Garden. And there's some information on that website. We're studying the question of, can a robot learn to tend a polyculture garden? Now, the monoculture, which is the way most agriculture is done, is where you keep all the plants nicely separated, and that's hard enough. But when you start to put different species together in close proximity, which is how polyculture gardening works, which has a number of advantages in terms of robustness to disease, allows you to use less fertilizers and pesticides, and also is better it reduces the amount of irrigation required. That's a huge challenge. So I actually don't know if the robot's ever gonna be able to do this. We've been working on it for over a year now, but I'd be happy to talk more about it. It's a work in progress. So I want to, again, thank the wonderful contributors or collaborators that I've had the good fortune to work with over the years, including Animesh right there, and thank my students and the collaborators at Berkeley, and also the sponsors of our lab. And with that, I'll be happy to take any questions. Thank you.
Wonderful. Thank you, Ken, for such a great talk. I think it covered so many bases, algorithms, very interesting choice of tasks, clearly. Manipulation is clearly sort of the open wide world with many interesting problems. So questions. Folks, for everyone who is listening to us on live stream, feel free to put in questions on the YouTube chat box. We can take questions from here. And folks who are live on Zoom, feel free to put questions directly in the chat box here. So one of the questions from YouTube is, have you considered a soft mesh morphing grasper made up of maybe a morphing physical 3D mesh, maybe out of continuum actuators? The mechanics or the mechanisms for develop such graspers exist, but clearly they have not yet made to robot learning or robot manipulation for grasping. So any comments and thoughts on that, Ken?
No, it's a great question, and here's my thinking on that. I know that there's a lot of groups working on different ways of using soft enveloping grippers, and I think it's very interesting. It can be used in a number of environments where you can also jam, let's say, small particles. Once you essentially conform around an object, then you use a vacuum to lock the shape of the gripper in place, and then you can lift the object successfully. What's interesting, there's two drawbacks to that. One is the wear and tear. That in a real industrial setting, or even a home setting, after a while, those systems can be prone to abrasion and puncture, so they deteriorate. And we just had a talk by Rob Howe from Harvard about this, and it's really interesting because that's a problem. It's a materials problem, and it's not clear, how to solve it. The other is actually more subtle, and it has to do with occlusion, where if you use this kind of gripper, you can get such a grasp, but it depends what you want to do with it next. So if you just want to drop it in a bin, that may work really well. If you want to do something with it, like in particular, identify what the object is, maybe find a barcode on the object, which is very, very important in industry, then you have a problem because you've essentially covered up a large surface area of the object. So that's why suction cups, which is kind of a sort of a form of this, is actually the gripper of choice for industry, because they just put this fairly small conformal contact, and then that leaves most of the object exposed. Now they do have some issue with wear, but then they solve that by essentially replacing the suction cup at a fairly regular, on a fairly regular basis. So I think there's a lot of interesting questions there. I also, the other question is, why not use more than 2 contacts? Maybe go to 3 or 5 fingered hands. And I think that's interesting, but I sort of come from the school of let's walk before we run. And what I mean by that is let's figure out how to do these grasps with 1 or 2 contacts, and then we can generalize to multiple contacts.
So we also have an interesting question from Kiros. Kiros is also on the faculty at computer science, and he works on computational sensing. He asked a very interesting question. Blind people are arguably able to grasp objects almost as well as the rest of us. So how do we reconcile that with the current state of the art on grasping?
Okay, good. Because that's a great thing I didn't mention, and that is tactile sensing. Blind people have incredibly, well-developed tactile senses, as you can imagine from reading Braille. And what they and actually all humans, and I think animals as well, use this feedback. Now it turns out, and I actually studied tactile sensing when I was an undergraduate back at UPenn, and it sort of was an interesting experience because I learned how difficult it was back then, and it's a very, very subtle and hard problem. Human capabilities of tactile sensing are extraordinary. We can detect, a sort of a sliver, a gap on a surface on the order of microns by rubbing our hands across it, but we have there's no systematic way of doing that for a robot, and it's been it's an ongoing line of research, just like looking at soft hands, and I hope we'll see some breakthroughs. I think that the gel methods have been very interesting, and using vision with internal reflections to essentially image tactile contacts. And I think there's some very interesting things going on there. And so you're right. I think that at some point we'll really understand that and then start to integrate that with the kind of methods I talked about today. I think that's really what's going to be needed to get to the really high levels of dexterity that you see in humans. And dogs, by the way. So a dog, I should have mentioned this, but I think of lately we just got a dog. And they have a parallel jaw gripper too. It's their mouth, okay, and they have a very elaborate way of manipulating and grasping things. And you hold up a strange object, and they figure out a way to get their mouth around it and to carry it. So again, this is a very subtle matter, is figuring out where the robust grasps are. And I think we're making progress. And I'm really excited, by the way, about this opportunity for robots to really, in the next, I believe in the next 5 years, we're going to actually see this happening in industry, that we're going to see robots being applied in very large scale to this warehousing problem. And I will add on that, I think it's a little different than self-driving cars, because in self-driving car, you have fairly low error tolerance. If you have error, even once every few hours, that could mean driving off a cliff. And in robot grasping, especially in warehouse contexts, it's fine to drop things every once in a while. In fact, humans do it all the time. And so the idea is it's not, you're not looking for that Six Sigma kind of performance. You need to get up around 95, 97, 98% success rate. And that is often acceptable for industry. They're also interested in time. They want to be able to very rapidly sense, compute.
We lose Ken.
Oh no! But he's still sharing his screen, so maybe he's still here.
He definitely is, but not sure what happened to his audio. Maybe let's give it a bit, and then hopefully he'll rejoin. He has joined.
What?
Ken, we skipped some audio for the past about like 15 seconds or so.
Okay. What?
Happens.
Oh.
Fair enough. So thank you, everyone. I think this has been wonderful. I am also seeing a bunch of questions, and I think if Ken is able to join us again, I have a next question that will probably be a summary of multiple of these questions. But I'm really hoping he can. Let's see. Deep sighs.
He's coming back. He's just thinking about the questions right now. It's okay.
I think
he's coming back.
Yeah.
There's so many great questions. Everyone has so many great questions.
Absolutely. I think network streaming error is a very good way of, oops, I dropped out, to think about this. No,
dramatic pause.
I think,
So, Animesh, maybe you can help Ken answer the question.
just give me
There was a great question in the chat box saying if we have the model of an object, why don't we directly merge it into the physical system instead of doing simulation? I think it's a very good question. So Animesh is not listening to me anyhow. So anyone who wants to answer, you go ahead. Flori is the host. You are obligated to answer.
I made Animesh the host.
I'd like to talk about Florian's question.
Yeah, I want to talk about that too.
Florian, do you want to say your question?
Well, the question is, we're starting to have differentiable physics engines where we can take derivatives of the state with respect to the parameters of the systems that we're handling.
Hello, everyone. Announcement. I just got a call from Ken. Unfortunately, there has been a complete network outage in his area. So there is no network. It is not his fault. He says there is no network at all. And I think we are also at the end of the hour. So I think I would like to thank Ken in absentia right now. And I did that over the phone as well. It was a wonderful talk. And at the same time, I would like to thank all of you for making this such a successful event. Thank you. And I say this on the behalf of Ken for the privilege of your time.
Thank you so much, everyone.
Kimberly, now all the follow-up meetings are canceled, are they?
I mean, I kind of think they have to be, since he won't be able to, if there's a network outage in his whole
So
neighborhood.
he did say he can call in on the
okay.
Zoom number.
Yeah.
So Kimberly, can you send him the phone number on the Zoom
Great.
meeting to call in?
Sending him right now. Thank you so much.
Okay. Okay, bye-bye.
Bye. Thank you.
Yeah.